Everyone for being here for our second high-end seminar of the term of the fall semester. So it's a pleasure to introduce our speakers today. Let me remind that we are recording this, so you can watch it afterward. Okay, again, welcome everyone. Our first speaker is Ole König. I hope I pronounced correct this time. Ole did his PhD on accreting compact objects at the Rameis Observatory in Germany with Professor Jorn Wilms, where he led the discovery of the nova fireball phase with Rosita, featured on the cover of Nature, and which was also presented here a couple of years ago, I think, in a seminar, one of these seminars. And also spectral time analysis of the Sirius X1 with NICER. As a member of the 60 simulator team, and as an external collaborator of the NICER team, is also involved in characterizing the new Athena, Rosita, NICER detectors. He's currently a SEO visiting scientist, but is going to continue with the postdoc position starting in the winter, so we're going to see him around a lot in the next few months, maybe years. And I think with this, the floor is yours.
Excellent. Yeah, thank you very much for this introduction and for inviting me to give this seminar. And I would like to begin this talk also by thanking Jack Steiner and his amazing group of students and Yushin, a postdoc who it has really been an amazing pleasure to work with during the last few months. And I would like to present this work, and it is on disk truncation in the hard states of black hole XR binaries. So to begin, I would like to introduce the outburst cycle of these transients. Transient low mass XR binary black holes, they go through a Q-shaped hysteresis during their outburst. So they start in quiescence and then rise in luminosity at roughly constant hardness, where they increase the flux in the power law component that presumably comes from a hot corona. Then at the tip, in the bright hard state, they transition to the left into a accretion disk dominated soft state, and they decrease by roughly 1 order of magnitude and then cycle back in this lower branch of the Q diagram into quiescence through the dim hard state. And throughout this evolution, the standard outburst theory of accretion disks predicts that there are changes in the inner radius. One thinks that in quiescence, the disk is highly truncated, and the corona is in the form of a advection-dominated accretion flow, and then at some point, the inner disk approaches the ISCO, and in the soft state, which I show here on the left-hand side, there is very clear evidence that the disk is at the ISCO. So you can see fits to a whole lot of a huge amount of RHTE data and other instrumental data, and you see that throughout the years, the inner radius was consistently constant to within 5% and what is believed to be consistently at the ISCO. Now, this is quite a clear-cut picture in the soft state. In the hard state, the truncation is much more debated. So there are basically two different opinions, I would say. People that rather come from the reflection spectroscopy side find that in this lower region, the disk is truncated, but then once one gets to the brighter hard state, it is quite close or at the ISCO. And this property is very useful because we can infer the spin of the black hole, assuming that the disk really extends to the ISCO. So this is one of the most fundamental properties, of course, of these black holes. So that's why it would be very nice if we can use this method. However, there are some other methods that have some other continuum fitting methods that have derived that the disk is actually highly truncated in this region of the Q diagram. And then when the source back transitions, I just want to briefly mention in the dim hard state, it is quite unclear where the disk truncation sets on again. And this is a somewhat understudied regime, mainly because it's at lower luminosity. So why do we have this debate? Why is there such a big discrepancy in the results? And the main reason is that we do not really know the geometry of the corona in the hard state. I would say at present there are two pictures mainly investigated. One shown here on the left-hand side is the inner hot flow corona, which has a truncated disk at maybe 10, but also higher radii. This model explains the variability very well. So, for example, type C QPOs, which are thought to be from lens steering precession, also models of the variability like propagating fluctuations, and also the recent polarization results from XP align very well with this model. However, it's not entirely clear one produces such a broadened iron line in the spectrum, and also often these models invoke a warm corona, which is not entirely clear where it's located and how it's stable over time. So that's the one model. The other model is a compact corona above the black hole, where the inner disk is at the ISCO, meaning that here we do not have significant, like high-scale truncation. This is consistent with the broad reflection, but the direction of the elongation of this corona along the jet axis appears inconsistent with the recent polarization results. This is a pretty big issue, I'd say. But there are also thoughts on how this plays together, basically. Another point that I'll briefly mention is the variability has suggested, the time lags have suggested that this picture involves some vertical moving of the corona. And now recently it has been also investigated whether this paradigm of soft lags unambiguously equal reverberation, whether this is also correct. Now, obviously, nature is more complex than a sketch. I think it is very clear that different aspects in the data, so the reflection, the time lags, the variability components, the polarization, they all probe different regions and different processes and different timescales in the accretion flow. And I want to flash up this amazing simulation here by Matthew Liska et al. Picking on some ideas that have been floating around in the literature a bit, that, well, perhaps we have a more complex picture and perhaps there is reflection on some cold blobs of material. And then the main disk is somehow truncated indeed. So there's certainly a lot to be investigated in the future theoretically and from the data-driven point of view, which I will do. And I think maybe this is a point where we can stop for the pizza. because I just saw that it arrived, and it will be okay if it got cold.
Let's take maybe 2 minutes break so it doesn't get off.
Working here for a while, you're trying to make friends.
I think I'll just continue and yeah. All right. So I would like to analyze and present the results on the outburst of SwiftJ 1727, which was a particularly bright, more than 7 crab bright X-ray transient that triggered coordinated observations with XB, NICER, NuSTAR, and other multi-wavelength telescopes. And there are 328 NICER observations that sample 3 of these main states: the bright hard state here on the top, the soft state, and the dim hard state. And what I tried here, and I would like to advertise a little bit the great work that David Horn, a student in Bamberg, Germany, does, who I supervise, to compare the NICER data to the RxTE outbursts of transients, in particular here, the X339-4. And you've seen it doesn't quite align so well. The bright hard state does, but then these states are much lower luminosity. So there's some thought that maybe the black hole mass is actually lower than what is currently assumed, the 10 solar masses. And Yuxin Zhang, who works here at the CfA, is currently investigating that. So stay tuned. And for completeness, because I think that's important for the interpretation, I'd like to mention the polarization results. So XB measured the source in the hard intermediate state, and there the polarization angle is aligned with the radio jet, which is interpreted as the corona being aligned with the plane, so horizontally extended. In my work, I use the continuum fitting method in order to derive constraints on the inner radius, and that works in the way that we can derive this radius from the amplitude, so from the flux in the thermal accretion disk. And that requires also an assumption on the distance and the inclination. But overall, this is quite a neat and very well understood technique that was developed beginning in the 80s. So another complexity here, and a whole bunch of physics that occurs in the accretion disk spectra are summarized under a topic called spectral hardening. This is Compton scattering that takes place in the accretion disk atmosphere that enforces a stronger Wien tail of this black body-like spectrum at the high energy end. And that generally means that the color temperature of the spectrum is larger than the effective temperature of the corresponding black body. And all of this microphysics is crammed into one color correction factor, which is the ratio of these two temperatures. So that has also needs to be taken into account. And on the right-hand side, you can see 2 example spectra in the data set, one in the soft state where we have really a disk-dominated spectrum, and one in the bright hard state where we have a more Comptonized dominated spectrum here. Let's have a look at the spectral parameter evolution. So how do these parameters change throughout the outburst? I used the simple model, which is a Comptonization model developed by Jack Steiner, and I used the EasyDiskBB parameter, the EasyDiskBB model in order to model the accretion disk. This is a model that assumes zero stress at the inner boundary, in case that is something you care about or no. But in principle, it models these 2 components that I showed before, the Comptonization and the disk. And what we see in the uppermost panel is the scattering fraction. So how many photons are scattered from the seed disk into the corona. And in the bright hard state, this is very high. We have a hard spectrum. The photon index is low, but is changing, is ramping up. The temperature of the disk is also relatively low, but it's also ramping up. Then in the soft state, we barely have any scattering into the corona. The scattering fraction is very low. The power law index is very soft. It also packs at the upper boundary because that component is basically almost not there. And then you can see that the temperature also decreases already here. So in this range, during this time, there is some data, but I'm not going to talk about this here because this was had some problems with the detector with the so-called light leak in NICER. But in these data, we didn't catch the peak of the temperature. And then the dim hard state, this kind of underexplored region there, the scattering fraction also ramps back up. The photon index decreases and the temperature also decreases. Now, the property we're interested in is the inner radius, which there are some differences here between these states. So the central question is, are we confident enough to claim a distruncation, or can we only give an upper limit because of the systematic uncertainties in the model and the data? So let's have a look about this in some more detail. If we derive the inner radius, assuming a color correction factor of 1.7, which is often found in the literature, then it seems, while there are some amazing trends here, we have so what you see here is the temperature on the y-axis, so hot disk on the top, cool disk at the bottom, this close to the black hole here, this far away from the black hole there. And it seems, okay, the source comes from out of quiescence, highly truncated and cool. Then it goes through the bright hard state where there seems to be significant truncation here. And then it becomes hotter, less truncated, turns around at some point. Then, wow, there's even some trends in the soft state and where we think it's at the ISCO, and then it returns through the dim hard state into quiescence. Now, we have to be careful. The spectral hardening, the theory of the spectral hardening, we know that this factor, this 1.7, is in fact temperature dependent. It is higher in when the disk is hot, generally speaking, in this regime, and lower when the disk is cooler. Does this change the picture? And the very clear answer is yes. And this leads to a significant change in the inferences or in the results, in the interpretation we derive from this data. So what we did here is now, instead of showing the radius basically immediately, we plot lines of constant radius with a temperature-dependent color correction factor when f scales with t to the 1/3. These are these lines here. And each of the lines are a doubling in radius. So if in the soft state, it is at the ISCO, then this is 2 times the ISCO, 4 times the ISCO, 8 times the ISCO. And you can see that suddenly this, what appears as quite a large truncation, like by a factor of 7, now shrinks down to a factor of 4 due to this temperature evolution. And in particular, in the soft state, we don't see evolution at all. It is very much on this line. This has been seen in other sources before. I think what is quite neat with this data set is that it really lies quite nicely on this 1t to the 1/3 line, which is quite a nice confirmation of the theory, I think. In the bright hard state, that's the contested area, we do see a trend that is at a different slope compared to this line. So there's some suggestive hints of a drift in radius. However, we somehow need to take the systematic uncertainties into account that go into this model. But this is really interesting. There's not a major truncation, but there could be some trends at relatively low values of like 4 times the ISCO-ish. And interestingly, trends like this have been also seen from other methods in reflection spectroscopy, for example, but there the error bars were often very large. This is like the size of the error bar. So often it was interpreted as, okay, we still assume it is at the ISCO, so we can measure the spin. But maybe there is some trends in mild truncation there. And the dim hard state, I will not talk too much about this here because there the signal to noise is lower, and there could be some traces of an onset of this truncation, but I think it is too early to say. But what I want to convey is that it is really important to take this temperature dependency into account. Because otherwise one may derive quite large truncation radii. And if we take that into account, we do not see that. So as a little outlook, I would like to mention what I did during my PhD. I analyzed the variability behavior of Cygnus X1 and other low mass exobinaries from the timing perspective, the variability. And we saw that there in this back transition, when the source goes from the soft state into the dim hard state, there are some really, really strong features that emerge in the time lag and the coherence. This has now also been seen in other studies, and no one really knows where these really come from. So what I'm really looking forward to when continuing to work with Jack is to explore this further, how we can basically combine these pictures from the variability and the spectroscopy side. And with this, I would like to summarize my talk. The first point is, it's kind of obvious, know what is assumed in your model. Truncation can change significantly from a factor of around 7 to 4. There may be drifts in the inner radius here in the bright hard state, potentially in the dim hard state, but we need to look at this a little further. As a final thought, if this is true, I think it's really interesting to think about these ideas. Maybe reflection probes actually somewhat a different region, like different blobs of material potentially compared to the continuum fitting. And how much space do we actually have between such an inner disk edge and the black hole with these data? Thank you very much.
So we have time for 1 or 2 questions. Any question online? Any question online?
Some just don't break the ice, I'm just interested. I mean, you say it's not a big factor, but a factor 4 is still going to change your spin measurement quite a lot, isn't it?
I think that's to be. I think it would, yeah, and I think it's to be explored how to how much that impacts the spin measurements, if this is really true. So it's interesting. Because these data points really are like at the tip of this Q diagram at the high luminosity end. So let's see. I think I don't want to make clear statements right now to not upset the reflection people, but it's interesting.
More questions? No, I have one. So you talked about tension between polarization models and observation. Do you think the polarization in radio or other wavelengths could help you disentangle this?
Yeah, that's the big hope, I would say. Yeah, there is already a lot of talk that this this alignment with the radio jet of the polarization angle and the conclusion that the corona has to be horizontally aligned, so with the accretion disk, that some people believe that that does put pretty strong constraints on some of these models, especially the above the black hole model, the compact corona model on the rotational axis. And I think it remains to be seen. There are a few other effects that haven't really been studied so well. For example, a polarization that arises from scattering in the accretion disk. So during reflection, basically, polarization that can arise from returning radiation from the soft underlaying disk. So I think there's a big potential to break some of these degeneracies to say something conclusive about the system, but it's also messy.
So what you say, perhaps, if I understand it correctly, is that the corona or whatever could change, or you have both something associated with the jets that will give you the vector polarization or whatever, and something associated with the disk, and depends on the accretion situation of the source, one might be more prominent than the other one.
That is definitely something that people talk about, yeah, that there are like multiple components that produce Comptonized emission, so multiple corona.
Thank you. If it's very quick, yes.
Thank you. I'm the outsider to this topic. So the question is that when you, I think from the soft state to the hard state, the changes of different parts of the disk, like the disk and the corona, are not at the same pace. So will this change the measurement based on the model?
So you're saying the evolution of the disk and the evolution of the corona are not at the same pace. And like asking whether that changes with the models. I need to think about that a little bit. I think that's a tricky question. Let's chat offline, I would say. Good.
Okay, let's thank all again. Let's move to the second speaker. Oh, why all does camera set up for us? Thank you. So let me introduce. So Kinjal is a fourth-year graduate student at the Astronomy and Astrophysics groups in Raman Research Institute in India. He examines astrophysical problems using X-ray timing, spectroscopy, and polarization properties in neutron stars and high-mass X-ray binaries. He develops tools and various diagnostics methods for the pipeline of the Indian X-ray polarization instrument POLIX on board the XPO-SAT. And I think he's going to be visiting here for...
Yeah, I'm visiting Jack till the end of this month.
Oh, okay. So yeah, if you want to have a chat, you have more time. And today is going to talk about luminosity dependence of multiple CRSF in BeXRB for you.
Sorry.
And future
Yes.
prospect with POLIX. Thank you so much.
Yeah.
For this.
Thanks for giving me this opportunity to present my work, and thanks, Jack, for hosting me. It has been excellent. So I would quickly start with the work that I do. So I work in high-mass X-ray binary pulsar. So this is like a huge main sequence star, and with a neutron star that is rotating around it. As you know, more massive the star, the stellar wind becomes exponentially more. And what you have is here is a lot of stellar wind coming from the high-mass main sequence star, and so wind accretion is the primary mechanism through which these neutron stars accrete. And due to the strong magnetic field, what happens is radiation is concentrated towards the pole, and that's where we get primarily of the emission from the poles of the neutron star. So the particular system that I'm going to talk about is called 4U0115 plus 63. It was it is a transient pulsar, so it goes into outburst. And so what this allows us to study the same system but across a multiple range of luminosity. So you basically use the same system to study what happens as mass accretion rate increases and decreases in the system, because most systems that are persistent hardly show any change in their luminosity over their life scale, probably by a factor of few. But here luminosity change can happen over a factor of 5 or more, 10 to the power 5 or more. So this was discovered with the Uhuru mission. It's a BE type star, as you can see here. It's a main sequence BE star with a very highly eccentric orbit, and this is a neutron star. And it has a spin period of 3 seconds, orbital period of 24 days, and with a moderately eccentric orbit. So this source is known to undergo multiple outbursts. Here you can see its outburst history with CGRO as well as BATC. Here you can see multiple outbursts in 78, 90, 99, 2011, 2015, and the latest one in 2023. So to say what is like the spectrum of these kind of sources, these are mainly dominated by power loss coming from the Comptonized emission from the accretion column. So if this is the neutron surface, this is near the magnetic pole. What we have is matter at these very high magnetic field strains of 10 to the power 12 Gauss gets matter infalling gets attached to the magnetic field, and they follow the magnetic field towards the pole. So we have kind of a column near the magnetic poles where majority of the emission comes. And at these high magnetic field strain, what happens is electron energy gets quantized and into Landau levels. And this is like a direct measurement of the local magnetic field strength. And in this kind of systems, this quantized energy levels show up as an absorption kind of feature on the continuum, which is like usually a power law spectrum. And that is what is known as CRSF, cyclotron resonance scattering feature. And this is what gives us a direct measurement of magnetic field close to the neutron surface. So moving forward, as I said, these are quantized energy. So you should see absorption not only at the fundamental, which is like exactly equal to say E0 minus E1 or E1 minus E2, but it can also show up as harmonics of this line. So, and this is one of the first sources which showed a lot of harmonics. So here you can see the first is the fundamental line, which is close to 12 keV. Here we also have the harmonics at close to 24, 36, and here 48. This is the Beko spectrum. And this is one of the first sources where people could discover many cyclotron, like not only the fundamental lines, but also the harmonics. One interesting feature that came up on this source was its variation of cyclotron line with luminosity. Here you can see the variation of the cyclotron line central energy with the luminosity of the source. And here we see at higher cyclotron, at higher luminosities, which is of the order 10 to the power 38 Hz per second, you have close to 11 keV where the line is. However, as the luminosity decreases, so this is how a typical outburst goes on. So the system is in quiescence, there is a certain outburst and die down. And here we can see that as the outburst dies down during the fall, you see the cyclotron line decreasing, but there seems to be a sudden step jump kind of a thing, like a transition between two systems that was observed by Nakajima. However, this was not expected. We either expect smooth increasing or smooth decreasing trend. There was so it generated a lot of interest. However, there were subsequent studies by Baldwin and Muller et al. In 2013, which showed that this might be due to like improper modeling of the continuum that gave rise to this kind of step jump system. Now, a paradigm shift came in the understanding of this source when people during 2011 outbursts with better angular resolution, with better spectral resolution of this source using Suzaku and RXT data showed that it's not that there is only the 12 keV line. There is another cyclotron line at 16 keV that is present at all times. So here you can see that it changes from 12 to 16, but they thought that this might not be true. There might be the two lines present everywhere, but one dominating over the other as the outburst progressed. And therefore, we can throw out this result because this is probably not the correct modeling. And subsequently, with Neustadt data also, this has been proven that indeed there are two cyclotron lines at all points of the outburst. So what we do is we take this new cyclotron line modeling of two fundamental cyclotron lines in the source, because as you can see, 12 and 16 are not multiples of each other. Unless we find a lower cyclotron line at 4 keV, we can't say that these are harmonics of each other. These are probably two fundamental lines. And what we do is we kind of use the new data, which is this data from RxT, subsequent new star data during the 2015 and 2023 outbursts to plot the results. Here on the top panel, you see the evolution of the 12 kV line and other subsequent lines at higher energies. This is a 12 kV line, 16 kV line, 24 kV line, the 34, the 36, and the 48. So what I primarily want to show is that instead of what like kind of a negative trend that we are now seeing instead a positive trend with luminosity. That is, as the luminosity increases, the line center of this CRSF also increases. And now, why this kind of increase happens? So there is a model called like the collisionless shock model that has been used to describe this kind of increasing trend. And that kind of theoretical model predicts that what happens is that with increasing luminosity, so usually what happens is there is a shock form in the accretion column of the neutron star, and that is the level at which we measure the magnetic field, which is like the source of this cyclotron line origin. And as the luminosity increases, it gets pushed down because a lot of matter is accreting, and this line gets pushed down. And therefore, we get with increasing luminosity, we probe basically deeper into closer to the neutron star surface. And if it's a dipole magnetic field, it means its magnetic field strength increases. So we get a higher energy. And the dotted line is the model that is there for the collisionless plasma model. And we can see here that the data and the model fits quite well. What we found out even more interesting is that for the 16 kV line and its harmonics, so the 16 kV line and the 32 kV line, you can see a kind of negative trend that is emerging after 10 to the power 38 kV. However, with one data point, it's hard to establish. So we hope that there are more observations of this source at very high luminosities, which are of the order 10 to the power 38. And so that we can establish that there is a critical luminosity. So this change from positive and negative correlation occurs at a critical luminosity. And if there are other data points around this, we can clearly establish that there is a critical luminosity present. But what's more interesting is that it's only present for one of the lines and its harmonics. It's not present for the other line. If you can see the 12 and 24 kV line, there is no such break at higher luminosities. Now, one thing to know is how the two lines originate. Like there are two fundamental cyclotron lines. It can originate in the same pole of the neutron star, like say the north pole of the neutron star at different heights, or they can originate from two poles of the neutron star. So how to do that? What we do is study the equivalent width of the line. So like if this is the continuum and this is the line, we take the area of this like the missing part, and we try to, this is kind of a proxy for the measure of the strength of the magnetic field. And as the neutron star rotates, so we see different parts of the neutron star surface. Here you can see that this pole dominates, but as it goes around and this pole comes around, we will see kind of different poles of the neutron star as the neutron star spins around its axis. So we calculated the equivalent width of the different cyclotron lines with the rotation of the neutron star for the two observations. However, here there seems to be some kind of correlation that here you can see that the 12 kV line dominates at, so more area means a stronger line. So more value of the equivalent width means it's a stronger line. And here you can see that in the second observation, at least we can kind of see a trend where the 12 kV dominates at a different position than the 16 kV line. However, this cannot be well established using the first data. So therefore, we can say that the two-pole cyclotron line model where the cyclotron line originates a different pole is a preferred model. But from this, we can't definitely say it. Now, one tool that will help us to better establish this is polarization measurement from like these two bands. So what I will introduce you to is the POLIX, which is a like polarimetric mission that I am a part of. This was launched on the name of the satellite is ExpoSat. It's one of the polarimetric instruments that was built by ISRO. It was launched on just like 1st January this year into a low Earth orbit, 650 kilometers, 6-degree inclination. And there are two payloads primarily in this satellite called POLIX, which is a medium energy X-ray polarimeter, and EXPECT, which is for timing and spectral analysis. This is the instrument. This was the satellite before it went for the launch, and this is post deployment. So what you see here is this is like the satellite axis, and here we have POLIX in blue, and EXPECT there are two such instruments on either side. Here you can see two modules, and there are two modules on the exact opposite side. So going ahead, this is the lab model of POLIX. Here you can see this is the collimator. It works in the energy range of 8 to 30 kV. It's a non-imaging instrument. It has a field of view of 3 degree by 3 degree. Here you can see like 4 proportional counter arrays around and a scatterer in between. Each detector has readouts from either end. So there are 2 channels each detector. And our MTP is approximately 8% for a 200 millicap source for 1 megasecond exposure. Because this is quite a background dominated instrument, as you can see, we don't have any focusing optics, and like there are shielding behind this proportional counters, but we experience a lot of background and it comes with its own modulation. So we have launched the instrument to try to see as a supplemental energy to IXP, so that we can kind of see the energy evolution of polarization parameters in like sources like neutron star and black hole. So this is our POLIX team. This is the PI of the instrument, and my supervisor, Professor Bishwajit Paul. And these are the rest of the team. There are PhD students, engineers, and a few guys from RRI. It was entirely built and from fabrication to everything was done at RRI, testing and all. This is what satellite looks like if you move one of the 4 detectors. So this is the collimator. X-ray enters through this axis. It gets scattered from the scatterer, and it's the photons get detected in one of these 4 detectors. These are wireframe detectors of xenon gas. I'm sorry, yeah, sure. So this is filled with xenon gas. These are proportional counter arrays, and there are resistive Nikon wires which can localize in which of these lines the photon gets detected. As you can see here, each line is connected, and the system works on the principle of Thomson scattering, where polarization after scattering from this very low atomic mass scatterer like beryllium gets reflected perpendicular to the polarization axis of the incoming photons. And the neutrons, and there is a rotation of the satellite that is to make sure that due to this square scatterer, we get less effective area away from the perpendicular axis. So the satellite also rotates at 0.2 RPM, so we can neglect the effect of like different effective area of post scattering. So what we expect therefore from the scattering is that if the X-ray photons are 100% polarized, you kind of expect 2 peaks at 2 perpendicular location. Like if this is the plane of the polarization, you expect more photons get scattered in this direction and exactly 180 degree opposite to it. And that is what the data initially shows us. These are very preliminary results. We are still doing the calibration and all. This is the spectrum we saw for CRAB. This is the 30 keV xenon alpha line, which is used for our system calibration. And this is the two hump modulation that we see that are exactly 180 degree apart. We can see that this kind of modulation can also be introduced through some reflection of the Earth. So CXB can introduce modulation, but to a much lower amplitude, just by reflecting selectively the photons from the Earth surface. So we're still in the calibration state, but we hope to use this instrument for measurement of 4U 1653 the next time it comes into outburst, so that we can say more definitely whether like the 2-pole cyclotron line model or at different heights of the same pole is the preferred origin of these 2 fundamental lines. We have already observed many sources. These are the few sources that we have observed: CRAB, Vela X1, SCO X1, Sen X3, GX301-2, Hercules X1, and Cygnus X1 and X3. And we are still ongoing the GN4 calibration of this source through GN4 simulation as well as blank sky observations. And yeah, please keep an eye out on the ISRO website for further updates. This is the website of POLIX, and this is my personal website. So if you have any question, please. Thank you.
Thank you. Questions?
Thanks, Kinjal. I just wanted to find out, are there any coordinated campaigns between POLIX and XP?
Not yet, so basically, till now we have guaranteed time for 1.5 years. But we want to finish the calibration of, once we are fully done calibrating, we would then go for coordinated observation with IXP, so we can kind of see that at 8 kV they match up quite well. So yeah, it's ongoing. So basically, due to the beryllium, we wanted, the less the better. So basically, lithium scatterer would have been like better. But what happens with lithium, it gets oxidized very fast. So we could not use lithium. Otherwise, the plan was to get 5 to 8 kV also, but so that we can better calibrate with IXP. But since we had to use beryllium, we will just be able to calibrate like kind of a trend, like energy resolved here and energy resolved with POLIX and IXP, and basically match the trend. That's a hope that we are planning to do.
Any more questions?
So what is the expected lifetime of POLIX?
The thing is that the expected lifetime is 5 years. We have, so after launch, we have enough fuel for it to go on for now. But as you know, proportional counter detectors tend to, like, there may be gas leaks or some kind of things like that happening, so that might reduce it. So other than that, we have stable detectors, and like till now, everything is going as expected. So I expect 5+ years at least. Yeah.
Thank you. Any more questions? Any online? No. So maybe let's try to close it in because there is CFA wide just impinging on us. Thanks. Let's thank all the speakers of today. Let's see next.